environment, and once it is released, it is considered free intracellular calcium. And once you have this free intracellular calcium, it will diffuse towards the troponin. And once it gets there, it will firmly attach itself to this troponin. And as a result, as we just said previously, the tropomyosin moves out of the way and exposes the attachment sites for the cross bridges, and then you get cross bridge cycling. And as long as you're in the contraction mode, the calcium remains attached to the troponin, and you get continuous cross-bridge cycling. Now, contraction is terminated, meaning cycling is terminated by the active pumping of calcium back into the sarcoplasmic reticulum. Now, the calcium is released initially by a passive event. So you release the calcium from the sarcoplasmic reticulum by a passive event, but you have to know it is actively pumped back into the sarcoplasmic reticulum, and that terminates cycling, that terminates contraction. Now, a very confusing point in the past has involved the ATPases involved in overall contraction. And you should realize there are two different ATPases involved. One is the myosin ATPase. Now, that's what we've talked about already. This is the cross-bridge ATPase. And this enzyme will break down lots of ATP during contraction, and that ATP broken down by this enzyme provides the mechanical aspects of contraction. Now, the second ATPase involved in contraction is the sarcoplasmic calcium-dependent ATPase. Now, this is the calcium pump on the sarcoplasmic reticulum that returns the calcium to its storage depots. Therefore, because of what I just said, you should realize that both the process of contraction and the process of relaxation are active events. The process of relaxation is considered an active event because you have to actively pump the calcium back into the sarcoplasmic reticulum. Now, a common question that students sometimes ask at this point is how many ATPs are involved in contraction? Now, there is no specific answer to that. There are two different ATPases involved in contraction. But you should realize if you are in the contraction mode, you have continuous cycling of the cross bridges, and lots of ATP will be broken down due to cross-bridge cycling. Therefore, then, trying to make it slightly quantitative, if one cross-bridge cycles one time during contraction, you would break down one ATP due to cycling. But if one cross-bridge cycles 1,000 times, you would break down 1,000 ATPs. More likely, thousands of cross bridges will be involved in muscle contraction, and they will cycle thousands of times, and therefore millions of ATP molecules will be broken down during the process of cycling. Just realize, as long as you are cycling, you are breaking down large numbers of ATP right on the cross bridges, and that energy released will go into the mechanical aspects of contraction. Now, a very important point that we try to emphasize is that in skeletal muscle, now this applies to skeletal muscle, in skeletal muscle, there are no calcium channels in the surface membrane. Therefore, since they don't exist, you cannot open them, and you cannot have an influx of free calcium. A very big point is skeletal muscle membranes, the surface membrane of skeletal muscle cells, does not have calcium channels. Therefore, no extracellular calcium is directly involved in contraction. All of the calcium involved in contraction in skeletal muscle is internally stored calcium. More specifically, most of that calcium is stored in the terminal cisternae of the sarcoplasmic reticulum, and that is a very important point. Now that summarizes contraction relaxation events in skeletal muscle. The next two figures here are more or less a transition from what we've been talking about into the mechanical aspects of contraction. Now just follow me through on this because I'm just going to make a few important single points on this figure here. Now this figure shows the mechanical events of contraction shown here. This is a mechanical twitch of the muscle. This is the electrical event shown on the same time scale. Now the electrical event is the action potential traveling over the surface of the cell and down the T-tubule. Now the main point here is, notice that this action potential that spreads across the surface and down the T-tubule, this electrical event is over before the mechanical event actually begins. Now this electrical event will release a small amount of calcium from the sarcoplasmic reticulum. This calcium will diffuse to the troponin and you will get some cross-bridge cycling, and these cross-bridge cycling will produce this mechanical event. Now suppose I generate a second action potential. I can generate and have completed a second action potential before this mechanical event begins. Now the major point here is a second action potential, a second electrical event will cause more calcium to be released from the sarcoplasmic reticulum. More calcium released means more cross bridges will cycle and we will get a bigger mechanical response. The more calcium you release, then, the more cross bridges that will cycle, and the more cross bridges that cycle, the bigger the mechanical event. Now, I can even have electrical events during the mechanical event right here. That would cause even more calcium to be released from the sarcoplasmic reticulum. The bottom line point is, if you have multiple electrical events during this mechanical event, you will saturate the interior with free calcium. And if you saturate the interior with free calcium, every cross bridge that can cycle will cycle, and you get the ultimate mechanical response, which is muscular tetany. Muscular tetany is just the situation where you saturate the interior with free calcium and you create a situation where all cross bridges are cycling. Now this is illustrated on the next figure here. In figure A, we're just showing the consequences of two action potentials per mechanical event. The second action potential causes more calcium to be released and the mechanical event increases. In B here, we have even more electrical events, more calcium is released, and C here is the ultimate mechanical event, which is tetany. You have saturated the interior with free calcium and the cross bridges are continuously cycling. Now there is a competition during contraction. You are releasing calcium from the sarcoplasmic reticulum and you're also pumping it back into the sarcoplasmic reticulum. If you are releasing calcium as fast or faster than you pump it back in, you remain in the contractile state. However, if you stop releasing calcium, then you will continue to pump the calcium back into the sarcoplasmic reticulum. And as we said earlier, it is the active pumping of calcium back into the sarcoplasmic reticulum that terminates the process of contraction. Now, one final point here, and we'll contrast this with cardiac muscle. Because the electrical event is very short compared to the mechanical event in skeletal muscle, it is possible to have multiple electrical events per mechanical event, and that permits muscular tetany. Whenever you can have multiple electrical events per mechanical event, that will induce muscular tetany. So because the electrical event is very short, it is possible to tetanize skeletal muscle. Finally, you should simply understand why it is possible to saturate the interior of the free calcium and tetanize skeletal muscle. Now that finishes off the first section here, excitation, contraction, coupling, and that brings us in to the chapter 2 here, which is skeletal muscle mechanics. I want to emphasize here that skeletal muscle mechanics are important mainly because they are a prerequisite to heart muscle mechanics. If you understand skeletal muscle mechanics, it makes heart muscle mechanics very easy. In fact, in the past I found the students who understand skeletal mechanics found it very easy to understand the basic points in cardiac muscle. Now we're going to start off here by going through a couple of definitions. They are preload and afterload. And of the two, preload is the most important. Now, simply defining preload. Preload, by definition, is a load applied to the muscle before the muscle contracts. If you apply a load before the muscle contracts, you are preloading that muscle, and the amount of weight you add is the preload. Now, when you add preload to a muscle, it does two things. First of all, the muscle will stretch. The greater the preload, the greater the pre-stretch of the muscle. Now, more importantly, the greater the preload, the greater the pre-stretch of the sarcomere. So preload will pre-stretch the muscle and also pre-stretch the sarcomere. Now, the other consequence of preload is the muscle will develop passive tension. Now, again, you don't have to have a good concept of tension. I simply think of tension as a force that develops in the muscle. Now, when we apply preload, we are going to quantize this preload by measuring it in grams. Therefore, if you put a 3-gram weight on a muscle then, before it contracts, we will assume that that will develop 3 grams of tension inside that muscle. And that 3 grams of tension is an internal force within that muscle. Just like with stretching then, the greater the preload on the muscle, the greater the passive tension in that muscle. If I apply a 10-gram weight to the muscle then, I get 10 grams of passive tension. Now, in muscle mechanics, there are 2 types of tension, and you have to keep these separate. This has always been a confusing point in the past. Now, passive tension is always generated by preload prior to contraction. Active tension, the other tension, is only produced during contraction. It is produced by cross-bridges cycling during the process of contraction. Now, when cross-bridges cycle, they don't have to produce active tension. But if you generate active tension in a muscle, it is only generated during cross-bridge cycling, which means it is generated during contraction. So just to summarize this then, passive tension is always generated before a muscle contracts. Active tension is only generated during the process of contraction. It only is generated during the process of contraction. Now, during contraction, the passive tension does not necessarily disappear, and therefore, and it's just a small point, the total tension in the muscle during contraction is usually the passive or preload tension plus any active tension you develop during contraction. Now, the other term here is afterload. Now, this is not as important as preload, but afterload, by definition, is the load you're trying to move during the process of contraction. You don't have to move it. It is the load you are trying to move during contraction. If you're trying to move a 100-gram weight during contraction, your afterload then is 100 grams. Now, the very important aspect to understand here will be length tension curves. Now, we'll develop these very carefully. Boards will probably not test length tension curves of skeletal muscle, but you have to be able to apply these curves to cardiac muscle. This material is the prerequisite material to understand cardiac muscle. Now, just starting off by looking at the axes here. On this graph, the y-axis has muscle tension. Now, as I said, you have to realize there are two types of tension in muscle. There's passive tension generated before the muscle contracts and active tension during contraction. Now, the x-axis is muscle length here. And we just put in muscle length units because we don't have to specify specific lengths.